relevant regions. They appear as a way to mimic the human visual system that, due to its selection capacity, can process a lot of visual information simultaneously. And to do that, they automatically learn the relevance of any element of the input, and they generate a set of weights that are then used to make the decisions. And those weights also help to increase the interpretability of models, because they allow us to understand where the models are focusing when doing the proposed task. So to map these scores, to represent these scores that represent the importance of each feature into the probability domain, these mechanisms use differentiable transformation that usually is the softmax function given by this expression here. In practice, it consists in applying the exponential function to each element of the input vector x, and normalizing these values by dividing by the sum of all these exponentials. And this normalization ensures that the components of the output vector sum to 1, and so it is a probability vector. But however, using softmax results in a strictly dense output, given that it attributes a probability mass to every element of the set. And sometimes this density becomes wasteful because it doesn't prevent irrelevant features to be considered, and that may affect the interpretability of the model. Also, until now, attention, and in specific visual attention, had only been applied to discrete domains. And in that case, attention may become too scattered over the image, and this may lead to a lack of focus. Getting back to the VQA sample, we saw that to answer the question, models use attention mechanisms to understand where they should focus. In a discrete attention model, the image is usually split in a grid, and each square is given a relative importance. And as you can see here, every image region is assigned to a non-zero attention probability value. And in this case, the model focuses on more than one region, and it seems to confuse this lamp with the TV screen, ending up giving a wrong answer to the question. On the contrary, in our work, we propose continuous domain alternatives to discrete attention models. Our solutions focus on both the continuity and the sparsity of attention distributions, and they can select regions that are simultaneously compact and sparse, such as these ellipses here. In this first case, we have an example of a continuous attention model that assigns non-zero values to every image region, but that it is more focused than its discrete counterpart. And for that reason, it answers the question correctly. And in this second case, the attention model is both continuous and sparse. And this sparsity allows us to single out the relevant features, assigning exactly zero probability to every region that is outside this outer ellipse here colored in white. So this means that all these regions outside this ellipse are not considered at all when generating the answer. Also, an important thing is that these attention maps are obtained without direct supervision on the attention mechanism. This means that the VQA models are trained only with question image pairs and answers, and the images do not have explicit object segmentation, and the attention mechanism automatically learns where it should focus. So to sum up our main contributions, we propose a framework to use continuous attention in images. And in this framework, an essential part is to have efficient algorithms to compute both the output and the Jacobian of our transformations. We focus on 2D continuous alpha and max attention mechanisms for the case where alpha is equal to 1 and to 2, but this will become clear further on. Then we introduce multimodal continuous attention mechanisms that allow us to model attention as a more complex and flexible distribution. And finally, we perform experiments on visual question answering that show that continuous attention helps to improve both the focus and the interpretability of models. Our code is available at this GitHub page, and part of this work was published as a spotlight paper at NeurIPS 2020. Also, 2 weeks ago, we uploaded a preprint on Archive about this third point, multimodal continuous attention. And in this talk, I'll start by explaining this first paper, and I'll also talk a bit about our recent results with multimodal attention. Okay, first I'm going to explain how discrete attention works and what we need to do to generalize it to continuous domains. So usually an image is split in L regions, for instance, these pixel regions, and it is represented by a value matrix V, or a feature matrix if you want, whose columns contain representations for each region. A discrete attention mechanism first computes a score vector F with one score per each element, in which high values correspond to more relevant parts of an image. So this region here should be the most important one in this image. Then a discrete transformation like softmax is used to represent this score vector into the probability domain, and we obtain a probability vector P. Finally, the discrete attention mechanism computes a context vector as a weighted sum between the representation of the image and the probability vector. And this context vector is the output of a discrete attention mechanism. Instead of assuming a finite set of objects or regions, we consider a continuous measure space as the R2 plane, and we represent the image as a continuous value function V. Instead of a score vector, we now have a score function F that can be mapped to probability density using continuous transformation, as I'm going to explain next. The output becomes the expectation of the value function with respect to the probability density. Okay, let's now see one step at a time to make it easier to understand. So to perform computations with a value and the score function, we need to parameterize them. And to do that, we choose the simplest solution, which is to consider linear parameterizations in terms of a vector of parameters and a vector of basis functions. So the value function can be parameterized as B psi, where psi are basis functions. And in our case, for simplicity, we always use Gaussian RBFs. And B is a matrix of parameters that we obtain using ridge regression. And this can be done offline because basically to smooth or to interpolate a discrete signal H, and in this case, it can be our original feature or value matrix, as long as we have the location of each region in the grid, to compute this matrix B, we just need to do a matrix product. And this is because this matrix G does not depend on the example and can be computed offline, previously. So as we already have the discrete representation H, at runtime, we just need to multiply H and G, and we obtain B. The score function corresponds to theta transpose phi, where phi are also basis functions, and theta is a vector of parameters that can be computed by a neural net. So, for instance, in R2, if we choose basis functions that are polynomials of degree up to the second, the score function is a quadratic form like this one. And this is the type of function that we always use in our papers. In what concerns the continuous transformation that maps the score function into a probability density, we use a framework called Omega RPM that is defined as the argmax of the expectation of the score function regularized by this convex function omega. And if omega is the Thales negative entropy that depends on this parameter alpha, we obtain alpha endmax. That in the finite case, when alpha is equal to 1, corresponds to the softmax function that we've seen in the beginning. When alpha is equal to 2, this corresponds to sparse-max, that contrary to softmax is a function that is able to output sparse probabilities. So the result may be a vector containing zeros. This happens because sparse-max returns the Euclidean projection of the input vector into the probability simplex, and this projection is likely to hit the boundary of the simplex, and in that case, the result is a sparse output vector. If S is continuous, and specifically if S is the R2 plane, we obtain what we call 2D continuous softmax when alpha is equal to 1, and when alpha is equal to 2, we obtain 2D continuous sparse-max. So for this quadratic score function that we've seen before, when alpha is equal to 1, the attention density is a Gaussian, and when alpha is equal to 2, the attention density becomes a truncated paraboloid with sparse support. So this ellipse here is a support of the distribution, and we only have zeros outside of the support. Finally, we need to understand how we can compute this expected value to obtain the final representation. And this leads us to one of the main contributions in our paper. So assuming that f and v are of the same form as before, so f is a quadratic score function and v has this form, when alpha is equal to 1, we show that this expectation becomes the product of Gaussians and can be written in closed form for the bidimensional case. In fact, we show that this closed form solution is also valid for an arbitrary number of dimensions. And this is nice if you're interested in, for instance, in attention mechanisms over higher dimensional data. When alpha is equal to 2, this case is more difficult than the previous one. So for 1D data, we can obtain a closed form solution, which is nice if you're dealing with, let's say, text inputs. For the 2D case, which is the one that we are more interested in, we find out a way of reducing the complexity of the problem that consists in reducing the problem to a 1D integral in the unit circle that can be computed numerically in a simple and effective way. For higher dimensions, I'm not sure if we can do something like this, but for sure it will require doing more mathematical derivations. We also show how to compute the Jacobian of these transformations, allowing for efficient backpropagation of the gradients in a neural net. I'm not explaining all these details here so that we don't lose focus, but regarding the existence of closed form solutions, we end up in the same situation as in the forward pass. Okay, at this point, we already know how continuous attention works, assuming that we have a score function f and the value function v. But we still need to understand how we can obtain these parameters theta. In our paper, we opt to use a merged setup where theta is obtained from discrete attention using moment matching. But this could be done in other ways without using discrete attention at all. An interesting detail is that our setup does not increase the number of parameters in a neural network when compared to discrete attention. So for 2D continuous softmax, where the attention density is a Gaussian, we can obtain these parameters by simply computing the mean and the variance of the discrete representation. This is possible because the covariance matrix of Gaussian corresponds to its scale parameter. But for the truncated paraboloid case, this is not as direct as in the Gaussian case, but we proved this expression here that allow us to obtain the covariance matrix from the variance. And this is not very important right now, but if you're interested in this, I can point you to the proof later. Okay, now that we already know how we define continuous attention, let's talk a bit about some of our experiments. So all our experiments in visual question answering use the same architecture that is based on a transformer, in which we change the parts related to the visual attention mechanism. And this table here shows that the results for the continuous models are very similar to the ones that we obtain using discrete attention, with a slight advantage of 2D continuous softmax. However, it is important to note that the number of basis functions used in the continuous models is around half the number of features that we use to represent each image in the discrete case. Perhaps more interesting is to look to the attention maps generated by each model. So these examples show that usually discrete attention is more scattered than continuous attention, and we already expected this, right? But as a result, this may lead to incorrect answers. On the other hand, continuous attention helps to improve focus on the important image regions. And 2D continuous Sparse is able to enclose all the relevant region inside its outer ellipse. For instance, you can see this here, where the model is, to answer this question, is a man wearing a hat. The model is only focusing on the region around the head of the skater. So generally speaking, we can say that the attention maps generated by the continuous models appear to be closer to the human judgment, which conduces to higher interpretability. But looking at the previous examples, you could be asking yourselves if it is a good assumption to think of attention as a unimodal distribution. Because in fact, it is true that there are cases in which this, let's say, simplified approach may not be enough to answer more difficult questions. For instance, in this example here, the question is how many planes are in this photograph, and you can easily identify two regions of interest that are far from each other. So you have this plane and this plane here. And if we consider a unimodal distribution, we would get something like this. And I think we can all agree that this is not very good. But what if we could consider distributions with multiple peaks or modes, depending on the input question and image? Yeah, and this is precisely what I'm going to explain next. So if you remember our definition of continuous attention, the output is an expectation of the value function with respect to the probability density P. And by the linearity of expectations, we can easily extend this definition to multimodal distributions that can be written as mixtures of simpler distributions. So in that case, the output of the multimodal mechanism becomes a linear combination of the outputs of different unimodal tension mechanisms. And the same thing happens in the backward pass. Although this definition is generic in what concerns the type of distribution we use, in this part we focused on the case where alpha is equal to 1, in which each unimodal attention density is a Gaussian, and the multimodal case corresponds to a mixture of Gaussians. An interesting fact is that our multimodal attention has some similarities with the multi-head attention introduced in the original transformer paper. So we can think of each component of the mixture as if it were a different attention head. And the key difference here is that in the multi-head attention scenario, these projection matrices that are learned as model parameters are head specific. So you have different matrices depending on the head. In our case, this matrix B here is fixed, so it does not depend on K. And the good thing is that this avoids head specific computations and enables a probabilistic interpretation of the resulting density as a mixture of densities. Okay, let's now see how we can implement this. So at this point, we have two open questions. First, how can we obtain these parameters, theta and pi, that define the mixture? And second, how can we choose the optimum number of components? So to choose the mixing coefficients and the means of covariance matrices of each component, we start from a set of observed image locations with their importance weights. And intuitively, the higher the importance weights, the more important the contribution of that specific region to the network's decision. But with this setup, now we cannot use moment matching to estimate all these parameters, as we've done in the unimodal case. So for multimodal distributions, we can think of this problem as that of fitting a mixture model to weighted data. And in that context, we adopt the expectation maximization, or the EM algorithm, that seeks a maximum likelihood estimate of the mixture parameters, and it is guaranteed to converge to a local maximum. So we adapt this algorithm in order to make it work with weighted data. And this is a very straightforward approach that we explain in our preprint on archive. So if you're interested, I can explain the intuition later. But what matters is that at training time, we pick the number of components randomly from a uniform distribution up to a predefined maximum. And in our case, we set that maximum to 4. This way, we expose the model to different number of components and during training, and we maintain the simplicity of the procedure, and we don't add runtime. So when k is equal to 1, we obtain the parameters using moment matching, and this is what we have done before. And when k is greater than 1, we run the EM algorithm for weighted data to obtain the final estimates. At test time, we compute the attention mechanism with an optimum number of components that basically is the one that minimizes these model selection criterion here that penalizes high values of k. And with this setup, we can now identify the main strengths of multimodal continuous attention when compared to discrete or unimodal continuous attention. So first, as we've seen before, unimodal attention models are limited to a single mode, right? And that they may face difficulties in complex scenes like this one, in which there are multiple regions of interest that are clearly far from each other. And in those cases, the continuous attention ellipses become very wide and less interpretable, or they focus on a single region and completely disregard the others. On the contrary, this attention map here suggests that multimodal attention densities tend to perform considerably better in such situations. So by increasing the number of components and setting the mean and the covariance of each Gaussian in a good way, the distribution becomes more flexible and capable of modeling more complex situations. Another interesting case is here in the bottom, where we can see that although there's a single region of interest, that region has a complex shape that confuses discrete attention that is very non-structured and scattered. Also, unimodal attention is overly focused and is not enough to fully encompass like all the relevant objects in the scene. And the attention map generated by the multimodal model seems to perform better, since it encompasses like all the regions of interest in the high probability mass region. So notice that in this case, the model opts to use 2 Gaussian components, and one of the mean is here near her hands, and the other is here near the red cup. as a side note, I just wanted to say that the results in terms of accuracy are approximately the same for all the models, even the multimodal ones. And I'm omitting them here because for these experiments, we retrained the models using improved image features that take into account the aspect ratio of the image. And for that reason, the results are not directly comparable with the ones that I showed before. But we've also done some experiments with human attention, and that's what I'm going to talk about next. So to evaluate how interpretable different attention models are, we compare the attention distributions obtained using different models with human attention. And to do that, we use the VQA hat dataset that contains human attention maps like this one that were obtained through a deblurring procedure. So human annotators were presented with a blurred image and the question about the image, and they were asked to progressively sharpen the regions of the image that helped them answer the question. To compare the attention distributions with the human attention, we measured the Jensen-Shannon divergence between the distribution generated by the models and the human attention. And these results, this table, show that the attention distributions obtained with multimodal models are more similar to human attention than the ones obtained with discrete attention. And even unimodal continuous attention performs a bit better. In this case, this is continuous softmax, to the continuous softmax. It performs a bit better than discrete attention. So this suggests that our method is able to generate more human interpretable attention maps. Here we have, it is the same example, but just wanted to say that this corroborates the idea that to look, to answer the questions, humans sequentially look for regions in the image until they found all the information they need. So our multimodal attention models replicate this process by identifying multiple regions of interest. To conclude, I'm going to sum up our main contributions and to discuss some ideas for future research. So summing up, we presented continuous domain alternatives to discrete visual attention models. And we presented 2D continuous alpha and max attention mechanisms and derived efficient algorithms for the case when alpha is equal to 1 and to 2. So in the first case, the attention density is a Gaussian, and in the second, it corresponds to a truncated paraboloid. And both cases allow us to identify ellipses in images in which both the location and the shape of the ellipse is controlled by the attention mechanism. Besides, we generalized this concept to multimodal distributions and experimented on visual question answering, which allowed us to obtain smoother attention maps than the ones generated by discrete models. Our work opens up interesting possibilities for future research in computer vision or in other areas like natural language processing. For instance, our attention models, by using fewer basis functions than features, may potentially be used to reduce the complexity of the self-attention module in transformers. And concerning multimodal attention, the first step would be try out different applications that could benefit from looking to different regions at the same time. For instance, tasks like visual counting or something like that. And another idea is to consider mixtures of truncated paraboloids, where the case where different components have disjoint support seems particularly interesting to study. Also, if the mixing coefficients are obtained using a sparse transformation, the training of models with a varying number of modes might be possible. Anyway, although we did not explore all these approaches, I'm free to discuss possible doubts you may have or suggestions. Thank you.
Thank you, António, for your presentation. So as António said, now we have time for some questions. If you want to ask a question, as usual, you can press the raise hand button and I will unmute your microphone. If you prefer, you can also ask questions through the chat. So any questions? So I have a question. You said that you had a maximum of 4 Gaussians, right, for the multimodal attention.
Yeah.
Did you try a larger number, a smaller number?
Yeah, that's a good question. So we tried like with 2 Gaussians and 3, I guess, but I'm sure we tried with 2. We didn't try with more because at least in visual question answering, we found out that like unimodal model is enough, and okay, it's not enough to answer all the questions correctly, but usually you don't have the need to look to like more than 2 or 3 regions to answer the questions. And even if you have like, for instance, in the counting question that you're asked to count like how many players are in the field and you have like 10, usually you can group them in like, imagine like 3 clusters, and it is enough to have like 3 Gaussian components around that area. Right. And that's why we didn't try with more than 4 components.
Right. I was asking this because I was thinking that maybe if you had more Gaussians with a smaller variance, with more like spiked Gaussians, you could have more complex shapes. You could model more complex shapes with imagine 5 Gaussians modeling the same shape, the same place, but with more resolution.
Yeah, and that's true. But then I think that we need to be careful about is that when you increase the number of Gaussians you use, you might end up in a situation that have like Gaussians that have like a really small weight in regions that you don't like. You're not interested in having Gaussians there. And so yeah, at the beginning it was easier to start with a small number of Gaussians, and then if needed we would use more Gaussians. Yeah.
Okay. So thank you. Now we have a question from Samuel. Samuel, I think you can unmute your microphone.
Yes. Can you hear me?
Yes.
Yeah.
Yeah, okay. First, good job, good work for your master's thesis. I think this is very cool, and I have some questions.
Sure.
More specific with the value function.
Sorry.
First, I must the value function.
Okay. Yeah.
First, I must say that this is my first time hearing this concept of continuous transformer and all this stuff. So my question is, for you to compute the value function, you need to compute first the discrete attention to extract the. So when you are doing the forward propagation of your model, you need first to compute the discrete attention, and then you need to compute the value function. So.
Yeah, that's true.
Did I understand everything, or I'm missing something?
Yeah, you're right. So actually, in our experience, we did that because that was like the first thing we tried. But we have, I didn't do that, but we have like in our first paper, we have experience in natural language processing where we don't do that. So basically there's the option that you can like smooth the signal at the beginning, and then you don't use the discrete representation. So you can do like, for instance, in this case where you use the moment matching to find the values of theta, you can like or the expectation maximization to find the clusters. There's a way in that, but that would increase the number of neural network parameters. But there's a way that you can obtain these, like the means and all of that. They can be computed by a neural net, so you don't need to use the discrete representation. But we did that for simplicity. Yeah.
Yes, and my second question is like, when you compute that, like when you are training, normally train with a batch. You are computing that for all the batch, or it's individual?
For all the batch. You can do that for all the batch, at the same time.
And did you notice like some difference? Because then when you're trying to do like I know that when you're trying to do the validation,
No.
you also do validation on batch, but you could, in the real life, you don't do batch, you do observation by observation, if you notice some difference.
Yeah, I'm understanding. Yeah, and if you're interested in like really demanding applications, or you need like the answer to be immediately, that could be a problem. I don't know, but in fact, you can, like as I explained in the slide before, you can pre-compute, like to smooth the signal. You just need to do a matrix product, because like one of the matrices, it does not depend on the example. It just depends on the shape of the image. So you can pre-compute all of that before, and it's not
But then you also need, but you also need to do that to every layer of the transform, or you just do that for the first layer of the transform?
No, you can, that matrix you just do in the first, but then when you need to smooth the signal, you just do like the matrix multiplication, and that you need to do every time you compute the attention.
Okay, I understand.
So basically, you add this matrix multiplication every time.
I see. Okay, thanks a lot.
Welcome.
Thank you, Samuel. Sorry. We have another question from Gonçalo. Gonçalo, I think you can. Yes. Okay. Hello.
Can you hear me?
Yes. Yes.
Okay. Hello. I have a question about the probabilities that you generate for images. Do you generate them per channel, or like for the red channel you have this region, or is it only
yeah, in this case we are working on a different level. So like we have the representation of the image is like a feature matrix that we extract using for instance a ResNet, and so we don't deal with the channels of the image. So basically you assume that the image is represented by a discrete value matrix or a feature matrix. For instance, imagine that I have like an image split in let's say 200 to be simpler, 100 squares. You have like a feature representation for each of those squares. So basically you have like let's say 2000 per 100 matrix, if 2000 is the channel dimension, right?
Okay. So the output probabilities that you generate is only
one per square.
Okay, so it's two-dimensional, right?
Yeah. So yeah, it's a matrix of, if you have like 100 squares, you generate 100 probabilities.
Okay, and I have another question. Could you possibly show again the slide about decomposing? You said you could decompose as products of Gaussians, and that it was applicable to any dimension.
Yeah. Let me just. Okay, yeah, that's it, right? So here I don't have the proof here for that, but I can show you if you want. I can show you. I have it in my master thesis. But the thing is that to compute this, expectation here, this is a product of Gaussians. The expectation in this case is a product of Gaussians. If you use Gaussian basis functions, and if the attention density is a Gaussian, so you're computing like the expectation of V and P, and everything is a Gaussian. So this expectation is a product of Gaussians, the integral of a product of Gaussians that has a closed form solution for any dimensions. So for instance, in NLP problems, this is like if you consider that text is a 1D input, you have a closed form solution. For images, a 2D input, you also have a closed form solution. And if you're interested in more dimensions, like 3, 4, 5, you also have the same closed form solution.
Thank you. I just didn't. Just wanted to remember better this part. Thank you.
Okay.
Thank you. We have a question on the chat. So Maxwell says, hi. In this featured representation matrix, why are some values negative?
So in the feature representation, you can have all type of values, because it's not it's not a probability distribution, right? So they don't need to sum to 1, and they can be everything. Then after applying softmax or another normalizing transform, that's the case where it becomes a probability distribution. And for that case, you just have positive values. And in the case of sparse max, for instance, you have like positive and 0 values, and they all sum to 1. But in the feature representation, they can be anything you want.
Okay, thank you. So are there any other questions? Okay, so I think that's it. Thank you again, António, for the presentation. Thank you all for your questions, and thank you all for
sorry, I saw there
sure.
a question. I can't. Okay, let me just. I saw there was one more question here. Yeah, the value have to do with the relevance. Yeah, it has. Yeah, that's true. But it's not like a probability distribution, right? Yeah, that's the thing. Sorry.
Okay, no, it's okay. Okay. Okay, so no further questions. So let's close it. Once again, thank you all for being here. This is it for today. We will be back in 2 weeks at the same time. So goodbye and thank you. See you. Bye.